Hello! Welcome to the Abbey Road Observatory. I'm your host, Jim, the filter guy. In this video, I will talk all about telescope mounts. But before we begin, please take a moment to hit the like button and to hit subscribe so you can stay up to date with everything the ARO is up to. Alright, let's get started talking about how mounts work. In this talk, I will give you an overview of the types of mounts that are available, as well as some background regarding how these mounts work. I will finish by sharing some of my personal experiences with a few different mount models. Let's start with a quick run through the list of basic mount types, starting with Type 1, human-powered. This type consists of simply holding the scope up in your hands. The type is very popular amongst old sea captains and has the quickest setup time. This mount gives the worst pointing accuracy and is impractical for large aperture telescopes. This type is meant for visual use only, but at least it costs you nothing. The next mount type is the standard camera tripod. To aim, you manually push or pull the tripod up, down, and left, right. Using a tripod is much steadier than by hand and permits a heavier scope to be used. Tripods generally are lightweight, portable, and quick to set up. It is, however, slow and clumsy to find and center objects using a camera tripod. Because a camera tripod is not motorized to follow the Earth's rotation, constant re-aiming is required. A camera tripod is suitable only for visual observing and imaging at very short focal lengths and exposure time. Camera tripods typically cost under $100 up to the low 100s. The next type is Alt-Az mounts with manual slow motion controls. They provide the ability to finally adjust your aim up-down, called altitude, and left-right, called azimuth. This gives one the ability to aim accurately while maintaining a quick setup. Being a manual mount means you still need to constantly re-aim the scope in both axes to keep your observing target centered. This mount type is good for visual observing and for imaging at very short focal lengths and exposure times. This type of mount can typically be purchased from under $100 up to the low 100s, although pricier models are available. Next are manual equatorial mounts, similar to manual Alt-Az, except the rotational axes of the mount are aligned with the Earth's axes, east-west and north-south, instead of left-right and up-down. As with the manual Alt-Az mount, accurate aiming is possible with this type, but one needs to polar align the mount and balance it prior to use. Again, being a manual mount means that constant re-aiming is required, but at least the mount only needs to move in one axis, the east-west right ascension axis. This mount type is suitable for visual observing and imaging at very short focal lengths and exposure times. These mounts range in price from under $100 to a couple of $100. The next mount type involves adding motors and a Wi-Fi enabled computer brain to an Alt-Az mount. Using a hand controller or the Wi-Fi connection to your phone, these mounts give you very fine control over up-down, left-right movement. As a result, very accurate aiming is possible. In fact, you can simply pick an object in the sky and tell the mount to go to it. These mounts are relatively quick to set up, some even coming with a GPS antenna so it can figure out where it is and the local time automatically. Once you confirm for the mount where it is pointing, it is able to track objects in the sky, compensating for the Earth's rotation. These mounts are great for visual observing, but can also be used for electronically assisted astronomy, so imaging at long focal lengths but using short exposure times only. They range in price from around $400 to just under $1,000. The final mount type uses the same idea of motorized computer control, but with an equatorial mount. As with motorized Alt-Az, you get very fine control over mount movement and accurate aiming and go-tos. Polar alignment and balancing are required, so setup time is longer, but in exchange you get the best tracking of all mount types. These mounts are good for all applications, whether you are a visual observer or a serious astrophotographer. They come in a broad range of prices, from around $400 up to over $10,000. An important reason for why there is such a large range of these mounts available has to do with the issue of load capacity. Here we have a range of motorized equatorial mounts sold under the brand name Skywatcher, a well-known and well-respected mount brand. These mounts all vary in physical size, but also vary in terms of how powerful their drive systems are, how robustly they are built, how much counterweight they have, and thus how much telescope equipment they can effectively carry. The value in kilograms shown here is the manufacturer recommended load capacity for each mount. Note how the price of the mount quickly ramps up with increased load capacity. Let's switch gears now and talk about mount drives. If you are at all serious about the astronomy hobby, it is likely that at some point you will own a motorized mount. For this reason, I thought it would be helpful to explain how mount drives actually work. Mount drives are required to deliver large gear reduction ratios. Tracking mounts move very slowly to match the Earth's rotation, but they are also required to deliver high torque. This has an impact on what drive types are suitable to use. There is also a lot of pressure to keep mount manufacturing costs low, which also impacts what drive types are used. There are several different kinds of drive in use today, all of which consist of some sort of DC motor combined with a mechanical gear reduction device. Let's first talk about motors. This is an animation illustrating how a basic DC motor works. The motionless stators on the outside are some sort of magnet, often a permanent magnet, but electromagnets are also possible. The spinny bit, called the rotor, has a series of electromagnet branches on it, also referred to as the armature. As the rotor spins, each branch gets energized in a sequence, creating a like and dislike magnetic poles that cause a repulsive or attractive force, respectively, between the stator and the rotor. Electrical current flows to each branch via a set of contacts called the commutator that rotates with the rotor. The speed of this motor increases with increasing voltage applied across the commutator. An increased speed means increased torque. A weakness of this design is the fact that brushes are required to rub on the commutator to complete the electrical connection, and these brushes wear out over time. There is also no feedback with this design as to where the rotor is at any moment in time. The big advantage of a basic DC motor is that it is cheap to manufacture. Any small toys or appliances that you have at home probably use this type of motor. Next up is brushless DC motors. For these motors, the design is flipped inside out, with the stators being electromagnets and the rotor being a permanent magnet. Digital circuitry controls when and for how long each stator coil is energized. This design requires no brushes. Speed is controlled by the timing of controller pulses, and more torque is achieved by increasing stator voltage. Since a digital controller is required to drive these motors, they are more expensive than basic DC motors. They are, however, more reliable and more efficient. Most new applications of DC motors, such as e-bikes and high-end cordless power tools, use brushless DC motors. The final type of DC motor relevant to mount drives is stepper motors. Stepper motors are a type of brushless DC motor. They have many stator coils and multiple poles on the rotor, allowing for the motor to be rotated precisely in discrete steps of a known angle. They require an advanced digital controller and are the most expensive of the motor types used for mount drives. They are, however, very reliable, giving repeatable, precise control over speed and position. Now that we have some motors to choose from, let's talk about reduction gears. Here is an animation of the simplest gear design, a spur gear. Torque is transferred from the drive gear to the driven gear via a single tooth, limiting how much torque can be transferred. The reduction ratio is calculated as the number of driven teeth divided by the number of drive teeth. One can stack multiple spur gears in a cascade in order to achieve a large overall reduction ratio, what would commonly be identified as a gearbox. Spur gears, because of the single tooth engagement, are prone to backlash, essentially slop in the gears, noticeable when you change direction. Spur gears are also known for their periodic error, a result of manufacturing tolerances causing every tooth of the gear to not be exactly identical. These weaknesses aside, spur gear drives are the cheapest to make, so they are very popular. Another common reduction gear design is the planetary gear. In this gearing system, the sun gear, shown here in green, drives the planetary gears in blue, which also engage at the same time with the fixed outer ring gear in gray. As the planetary gears orbit around the ring gear, the carrier to which they are attached, in red, also spins around and forms the output from this gear design. The reduction ratio is calculated as the sum of the sun and ring gear teeth divided by the number of sun gear teeth. If you stack multiple planetary gears, using the driven gear of one as the drive gear of the next, you can achieve very large reduction ratios. Planetary gears require ample lubrication to function normally, and they are prone to backlash and periodic error like spur gears. They are, however, capable of transferring large torques, which makes them popular for applications like automobile transmissions. The next gear system to consider is the worm gear. The drive worm has a spiral groove cut into it that engages with the worm wheel. As the drive worm rotates, the worm wheel teeth are carried along by the grooves in the drive worm. The reduction ratio is calculated as the number of worm wheel teeth divided by the number of spiral groove starts on the drive worm. A worm gear drive gives a large reduction in a single step, but they need to be well lubricated to function normally. They are also prone to backlash and periodic error, but these are easier to manage than with other drive designs because there are fewer interacting parts. One advantage of worm gears is that they can't be back driven. The friction between the worm and the worm wheel is too great for the wheel to turn the worm. This makes the drive fail-safe, meaning when the power is off, the mount won't move under the weight of all the mounted equipment. The final gear-based drive to consider is the harmonic gear, also called a strain wave gear. This reduction gear design was originally invented by Walton Musser in 1957. One notable usage of this gear design was to drive the wheels of the Apollo mission lunar rovers. They have only started to become popular for telescope mounts in the last couple of years. In this design, an elliptical-shaped wave generator, shown here in green, deforms a cup-shaped flex spline, shown in red, as it rotates around. The flex spline is deformed to the extent that it engages with a circular spline, in blue, on the outside of the assembly. For every rotation of the wave generator, the flex spline advances 2 spline teeth. The resulting reduction ratio is calculated as the number of flex spline teeth divided by the circular spline and flex spline tooth number difference. The harmonic gear is able to deliver a very large reduction ratio in a single drive step. Harmonic drives are significantly more expensive than other drive types. They can be back-driven, i.e., not fail-safe, and their periodic error is not better than other drive types. Their advantage is that they have no backlash and deliver high torque at a large reduction ratio in a small size. The final speed reduction method to discuss is belt drive, whereby a flexible toothed belt transfers torque between the similarly toothed drive and driven pulleys. Reduction ratio is calculated as the number of drive pulley teeth divided by the number of drive pulley teeth. Because of the space required, belt drives are typically only used for small reduction ratios, or when it is desirable to have a large separation between the drive motor and the mechanism being driven. Belt drives are sensitive to cold temperatures, and the belts eventually wear out and break. They, however, have no backlash, can deliver high torque, and have low periodic error. We now have a library of DC motors and reduction gears to choose from. Let's look at some example mounts to see what sort of drive solutions have been applied by their respective manufacturers. My first example is of the first fully motorized mount I ever owned, the Orion Atlas EQG, which is essentially a rebranded Skywatcher EQ6. I found this to be a very sturdy and reliable mount. I am intimately familiar with the drive system for this mount because I upgraded it myself to a belt drive. After many years of service, I sold this mount and replaced it with a larger one. This mount's drive consists of 2 DC stepper motors, shown here, the image on the left, driving 3 brass spur gears. You can see 2 of them here, and the other one goes on the end of the drive worm. So they drive a steel worm, which then moves the large brass worm wheel you can see in this image here. Using a kit I purchased, I replaced the 3 spur gears with a belt drive, which you can see part of it here, in order to improve backlash and periodic error. By the way, this mount at the time sold for around $1,500 to $2,000 Canadian. My next example is of the first Alt-Az grab-and-go mount I owned, the Ioptron Cube Pro. It is quite small and lightweight, which makes it perfect for taking to outreach events or to my cottage in the summertime. It gave me acceptable tracking and go-tos for doing visual and electronically assisted astronomy. I cracked the mount open to do some customization, swapping out for a better dovetail shoe, improving the friction on the declination clutch, and adjusting the backlash in both axes. Eventually, I sold this mount to get something with more load capacity. Its drive consists of 2 basic DC motors. You can't see them, they're enclosed in the plastic enclosure here. Driving multiple plastic spur gears, which you can see here. Plastic being known for its durability and high accuracy. You only use plastic when you want it to be cheap. The plastic gearbox drives a brass worm, you can see here, which then drives an aluminum worm wheel, you can see right here. The drive also has an optical encoder, also hidden inside the white plastic enclosure with the motor. That is to keep track of where the drive is pointing, since there is no position feedback provided by the motors themselves. At the time I bought this mount, it was around $400 Canadian. The mount I replaced the cube with is the Meade LX65, another motorized Alt-Az. Even though it has a significantly larger load capacity than the cube, it is still relatively lightweight and portable, and is quick to set up. I found the tracking and go-tos with this mount to be pretty good, and I used it regularly for electronically assisted astronomy and solar imaging. I especially loved the dual saddle arrangement, allowing me to mount 2 telescopes at the same time. I did have to do some repair work on this mount when the declination drive seized up. Turned out to be a lubrication issue. I presently have this mount listed for sale, as I have decided to replace it with an equatorial mount. This decision being driven primarily by the fact that Alt-Az mounts do not track well when looking directly overhead. You get something called field rotation. The drive for this mount uses 2 basic DC motors. You can see there's one here. I can see them both here. There's one there and one there. Driving 3-stage steel planetary gears. They're enclosed in this darker gray enclosure here, and you can see them here, there, and there. Followed by 2 brass spur gears. You can see they're there, and up close. You can see them here. That drives a brass drive worm. You can just see there, which then drives the aluminum worm wheel. You can see clearly in this image on the left the adjustment screw for tuning the worm gear backlash. So the screw right here pushes on the whole assembly, adjusting how hard the drive worm is connected to the worm wheel. The drive also has an optical encoder on the end of each motor to tell where it is positioned. You can see the wires for it coming out here. Here and here. I bought this drive for just under $600, but they now sell for more than $700. My next example I gave in a previous talk. It is called the Ioptron Sky Hunter. It is very small and lightweight. I have found it to have good tracking and accurate go-tos. It can be used in either Alt-Az or EQ modes, and there are several options available for user interface. A traditional hand controller, connection wirelessly to your phone or tablet, or simply by using the buttons on the side of the mount. My only beef with the mount is that the right ascension clutch is a little wonky. What I mean is, it is possible to tighten the clutch easily, but then it requires an inordinate amount of force to loosen it again. I successfully transported this mount in my luggage to Mexico for the 2024 total solar eclipse, and I have used it multiple times for electronically assisted astronomy. This mount's drive consists of two basic DC motors. You can see there's one there and the other one over here, and there's a close-up here on the left. And they drive multiple metal spur gears. You can see there's a close-up here, followed by a belt drive, which you can see on the end here. That belt drive, in turn, drives a brass worm. You can kind of see there, a sliver of it, which then drives an aluminum worm wheel. The optical encoder in this particular design is clearly visible on the back of the motor. You can see there's the daisy wheel and there's the sensor right there. The basic mount costs just over $400, but I added the optional hand controller and adjustable base, bringing the total price closer to $700. The newest mount in my collection is the Jouet 17, my replacement for the LX65. It is a Chinese-made discount harmonic EQ mount. Brand-named harmonic mounts in this load capacity range, such as the ZWO AM5, tend to cost in the $2,500 to $3,000 Canadian range. I purchased this mount for $1,400 off of AliExpress. It is quite portable, being fairly small and lightweight, but it also delivers high torque, being able to carry up to 13 kilograms of equipment with no counterweight. The mount delivers good tracking and accurate go-tos, and is super quiet. You pretty much can't hear it when it moves. The mount uses an open-source control board and firmware called OnStep, and comes with a dinky little, but functional, hand controller. The mount also has built-in Wi-Fi and Bluetooth as alternative ways to connect to the mount, but I found these methods unreliable. Connecting the mount to a PC via USB cable was a much more reliable way to control it. I have had an opportunity to use this mount several times now for remotely located electronically assisted astronomy, and it worked great. Out of curiosity, I cracked the case open to see what was inside. This mount uses two stepper motors. They're stacked one on top of the other. There's one here and there's one underneath. Connected to harmonic gears. That's what's in the little puck-shaped area here and here. That's the harmonic drive part. They're motor and harmonic drive connected to each other via a belt drive, which you can just make out. There's one here, and the other one's here. My last example is the Skywatcher EQ8R Pro. This is a beast of an EQ with miles of load capacity, 110 pounds worth. It is absolutely not a portable mount, the head alone weighing more than 50 pounds. This mount gives excellent tracking and go-to accuracy. It also has performed well for me down to minus 25 degrees Celsius. This mount is permanently installed on a pier in my backyard, and at any one time has an assortment of 2 or 3 telescopes mounted to it. I have not dared to open my own mount up, but I did manage to find a video on YouTube showing what it looks like on the inside. It uses 2 honkin' big stepper motors. There's one there, and there's the other one there, about the size of my fist. And they are either directly driving a worm gear, as you can see here in the case of the declination axis, or connected to the worm via a belt drive, you can see here, for the right ascension axis. Despite using stepper motors, the mount also has additional sets of optical and magnetic position encoders. You can see there's a sensor here, and there's a strip that goes around here. It's a magnetic location sensor. So they've added that for additional pointing accuracy and the ability to move the mount by hand and have it still know where it is pointing. I purchased this mount, just the head, for $4,500 Canadian in December 2019. It now sells for $67.50. Adding the appropriately huge tripod brings the price tag up to $8,100 Canadian. So, that is about it. You are now up to date on my experience with telescope mounts. Hopefully, you will now have a better understanding of how mounts work. In parting, I have a few last tidbits of wisdom to share with you. Your enjoyment and success as an amateur astronomer relies heavily on you having a good mount, one that is solid, performs well, and is appropriately sized for your application. It pays not to cheap out. Get as much mount as you can afford. You will thank yourself later. For visual observers, an Alt-Az mount with slow motion manual controls is probably good enough. However, if you can afford a decent tracking mount, that is even better. For electronically assisted astronomy and solar system imaging, you are okay using a motorized Alt-Az mount, but you may meet with some limitations such as maximum sub-exposure time and field rotation, so a motorized EQ mount would be better. For long exposure imaging, i.e. sub-exposures longer than 30 seconds, you will want a solid motorized EQ mount. Remember to pick a mount with a load capacity greater than what you plan to mount on it. Well, that is it. Thanks everyone for listening. If there are any questions, please feel free to comment on this video or send me an email using the address listed in my channel description. Don't forget to click like if you like this video, and to subscribe to my channel if you want to see more videos from the Abbey Road Observatory. Bye for now.